Hi, everybody. Welcome back to another episode of Robo Papers. Today we have Haoyu Zhang sharing with us his paper, TesserAct, Learning 4D Embodied World Models. Thank you so much for making the time, Haoyu. And Chris is rushing to join this podcast, so he should hop on quite soon. But we thought we should just start first. Maybe, as a start, Haoyu, if you can share with us a little bit about yourself, how do you get into this kind of research in the first place? That'd be great.
Okay. So first, thanks Robo Papers for invitation to introduce my paper. And I'm Haoyu Zhen. Currently, I'm a PhD student at UMass Amherst, working on building 3D foundation models like large language models or world models. My supervisor is Professor Chuang Gan, and I also collaborate with Professor Yilan Du. Okay, nice. So this is our new released paper, TesserAct, and it's for the embodied world models. So maybe 2 years ago, we are focusing on building embodied foundation models, and we are thinking about what's the architecture for the embodied foundation models. They can be large language models. Then we design some 3D LM or 3D VLA to combine large language models with some 3D understanding capabilities. Then the robot can interact with the 3D physical world. And then we find that there may be some generalization ability for language model in robotics community. And then we see the emergence of world model like Sora. When we saw the release of Sora, it was like, wow, can we use them into the embodied AI community? We try to working on some video diffusion models to build embodied world models. Okay, so let's move to the paper today.
Yeah, I guess maybe just really quickly for even those like maybe not non-researchers who may be listening in, can you describe exactly what do you mean by world model? Is it like a case of generating videos? And what do you mean by 4D, if you can?
Yeah, that's a great idea, and it's also the motivation of this paper. So first question, what is the world models? It is just a model that predict videos. I think for the definition of world models have three main abilities. So for the first thing is that world models takes action as input. This action can be textual, like instructions provided by user, like pick up the cup, or it can be in a position or rotation of the end effector, and they are in floating numbers to control the robot to move. Then the world model can generate a video. And another main ability is that the world model can predict the future states. Like for our work TesserAct, it can predict videos. Or for our 3D VLA work, it can predict the goal image. So a world model need to reveal some future states. And the final ability is that the world model should interact with the world. So you can see the demo here. It can grasp the apples and cups for any given scene. So this is the definition of world models, and it's pretty cool. It's a good idea to working on. And the second question is that what is 4D? It's really simple. For the 3D is that our 3D world, and the 4D is just add the time space to it. So it's a dynamic scene. So 4D world model is that we want to design a world model that can predict the dynamics of the environment. That is.
Yep, got it. Cool, perfect. Yeah.
And okay, so that is super straightforward to maybe talk about some motivation of our TesserAct. So it's maybe into two folds. For one thing is that why we choose world models, and another one is that why not use your 3D representation? Why we choose time space here? So maybe 2 years ago, introduced 3D-LLM and 3D-VLA. There are some large language models to interact or understand the 3D scene. Then we can predict some action for robots. But we find that there's no generalization ability for this 3D language model. Like if we change another scene different from our training set, the results are really biased. We noticed that for a video model, we can mitigate this challenge. So you can see the results here. All this image or all these videos are collected from Unsplash. It's never in our training set, but our video diffusion model can generalize well. So this is why we choose word model. And another one is why 4D or why 3D plus time is that like many robot paper, their input is image. But for this paper, for this work, we don't know the robot arm. We don't know how to move the robot arm to the precise position. So another modality is important, which is depth map. So we add another modality, time and depth, to traditional works. And this is why we introduce 4D concept.
Got it.
And
So sorry.
okay. So to begin with, we can first watch the demos here. Like it's really cool. Like we can generate a 3D scene, and our models just borrow the knowledge from video diffusion models like Sora, View 3, something like this. And it's generalized and cross multi embodiment. This is our new works.
So literally, when given a single image representing, let's say in this case, this guy in front of the laptop have a can of drink in front of him, just by prompting with the language, basically the 4D world model will imagine for the next, I think 49 frames or something like that. So like a couple of seconds, I suppose. Right, in your paper, like what should happen given the instructions, and then just imagine that. And you say basically you use RGB, but I think you use depth and also normal, right? So maybe you can talk us through the whole setup of the architecture. How do you go about training the thing? Some of the consideration when how you set up the whole architecture.
Okay, so let's move on to the papers, and let's provide some more details about the architecture. I'll see the PDF here. Okay, nice. So this is the overview or the training architecture for TesserAct. So we borrowed the CogVideoX backbone for the main part.
Yeah, could you share a bit what is CogVideoX for those who don't know what is it?
Sure. CogVideoX is a video diffusion model like Sora. It's a general purpose for video generation. User can give a description of the scene, and then CogVideoX can generate a video based on the user's input. Like this is the results from CogVideoX, and the input is that a man drawing maybe in a sunset scenario. So we design our architecture based on CogVideoX, and then we add 2 additional projector. For one thing is depth projector and normal projector. So we make some addition we just use add operator here, and then they're all given to the cog video's backbone, which is a diffusion transformer. And then finally, we can get the RGB output, depth output, and normal output, and we supervised on this output. So training video diffusion model is really challenging. Like, there's many settings we can choose, like using LoRa to fine-tune the cog video X backbone, or just do some SFT on the backbone. So for here, we use SFT to train our TesserAct on a large-scale dataset. So for the dataset, it's in table 1. We use some synthetic data from a simulator called RLBench. It can give a precise depth and normal annotations. And also we use some real-world data like RT1 proposed by Google, or Bridge dataset proposed by UC Berkeley. And we also use human and object interaction dataset, something V2, to make our model generalized well. So we annotate these video datasets with depth and normal to train our.
And so typically these videos, when you say like 80,000 videos, like 100,000 videos for something video, typically each of these video, I imagine, lasts for maybe a couple of seconds, doing a very specific, like, short task, I suppose.
For the video, the length can be maybe 150 frames per video. So that can be 8 seconds long. It depends on the FPS. So it's a really large scale dataset, benefit from OpenX. And we can also watch some more results to see more results from TesserAct. And this is our galleries. Like for each result, it can generate a great point cloud, 4D point cloud. So a robot arm moving and grasp the objects.
I saw in your paper you guys actually purposely didn't use point cloud and just basically referring depth and normal, right?
Yeah.
You mentioned something about the trade-off. Maybe you can share a little bit about that.
To get a point cloud is just straightforward, since we have the depth map. So we can project the depth maps into the 3D space, then we can get the point cloud. And the point cloud is like here, and it's just projected by depth map. And I will also show how we project depth map later. So we can first see the capabilities or some results of TesserAct. Like, we can, for each scene, for each given image, we can generate action-rich videos. Like, we can prompt with different instructions, like pick up the sponge, or use the sponge to clean the table. We can get different video results, and it's photorealistic. Also, this is another example. Like, we can pick up the different objects, the green apple or the red one, and also for the soft bodies.
I'm curious about the specific robot. Like, so I saw the Google robot, and then sometimes it's Franca. So does it mean that your starting image already have like part of the Franca, and therefore imagine it to be a Franca? Or in your text prompt, you actually say something like use a Franca arm?
The prompt, user can decide which robot to use. Like, if you want to generate a video act by Google Robot, you just add Google Robot in the prompt. Then we can generate a video of Google robot. And if you want to use Franca, then just add Franca at the end of the prompt. So this is the video here. Like we showed multi-embodiment part here. Like for this scene, it's a Ghibli style image. We can prompt by Franca or prompt by Google robot. And another one is the real world image. You can also use a chosen middle X. This robot arm is used by bridge dataset, so we can also condition our model on different robot arm. That's really interesting, and it's like digital twin. Like we can use two different arm to do the same tasks.
Yeah,
also,
I suppose you are able to do that because the underlying dataset have all these specific robotic arms or robotic embodiment.
Yeah. Like different datasets use different robot arms, so that's benefit from datasets, and diffusion model can learn about it.
I'm curious. Also, by the way, Chris is here. Yo, Chris, feel free to jump in and start asking questions.
Hi, Chris.
I'm curious, like how much resources is used or compute is used when you're training this this world model? Because as you mentioned, the dataset is not lots.
Yeah. Basically, we train our TesserAct model by about 16 A100 GPUs for 3 weeks. Yeah, that's really time consuming and also use a lot of GPU resources. But this is how we get a pre-trained model. And now we are working on designs on LoRa fine-tuning on TesserAct. Then other institution, other people can train our model easily. Maybe just use 4 GPU to train our model by 3 days. We are still working on it. And another feature.
How much data do you think you'd need to add a new robot embodiment? How much data do you think you need?
For pre-training our model, maybe at least 100,000 videos. But to LoRa fine-tune our TesserAct, maybe 100 videos is enough. So we are still testing the LoRa fine-tuning. So maybe stay tuned and we will update our GitHub soon.
That's good.
Then everybody can not using TesserAct for inference, they can train TesserAct for their own data. That's promising.
Yeah, so I guess
so you
after
think,
you
like,
train up this.
Sorry. So like with 100 examples, would that be good enough for me to like train a diffusion policy on the outputs or something? Is that the idea? Or like what would it? I guess what would you expect from 100 examples or something for LoRa fine tuning?
I mean, for fine-tuning our video diffusion models, fine-tune our maybe this part, like this video diffusion model is to predict videos, and you can only use 100 videos to LoRa fine-tune and get a great results.
Yeah.
And for the policy model, 100 videos or 100 samples is still it's also enough. Yeah. But for pre-training to pre-training 4D world model, we may need many data samples, at least 100,000. And we may discuss this later, like we try many training strategies for pre-training stage. Like we use LoRa fine-tune on this dataset, but the results is really bad, and the depth and normal modality works not well. So we need to fine-tune all the parameters in a big video diffusion models like Cogvideo X. The parameters of it is like 5 billions or 5 billions. But we find that if we already have a great pre-trained model like TesserAct, then you can do some really easy setup to LoRa fine-tune it, get great results on your own data. That's what we find. So
Is that
that's
partly
really good.
so 100 is like shockingly small to, in my opinion, for like fine tuning like a world model. So it is part of that data efficiency because it's a 4D model because of the depth. Is that
Yeah.
or something else? Or am I wrong?
Yeah.
Okay, yeah.
And I also recommend in very early stage of our project, we try to use LoRa fine-tune on Cogvideo X only. Like for here, we add many projectors and many new modalities to 2D video diffusion models. But if we don't add these modules, we can use LoRa fine-tune on 50 videos to get a really good results. Maybe like these repositories, fine trainers. Fine trainers is a great repositories for training world models or diffusion models, and they find that if you want to use a lot of fine-tune on diffusion models, 50 videos is enough to replicate Pika effects like this. They only use very small video samples to replicate these effects. But for our project, we want to design a 4D world models. Then we need a huge amount of
Sorry, just to double take on this 100. What you're saying is that once TesserAct is pre-trained well, then you can LoRa fine-tune on a lot less, right? Let's say 100. And so those 100 videos would, I imagine, involve one specific robotic embodiment doing one task, something like that, right?
Yeah, something like that.
So it's like you have maybe 100 a new 100 videos of, let's say, the Google robots pouring a cup of tea, right? So you 100 videos of that, and then from there you should be able to imagine, again, like different kind of cups, but still basically different kind of like drinks, something like that, right? But you won't be able to, let's say, use get Google robots suddenly to imagine playing tennis, even though it might be right.
Yeah.
Okay.
Like TesserAct can, since we train RT1, so for some tasks like pick up different color cups, like that'd be good for RT1. That'd be good for TesserAct. But if you want to generate some videos of another robot arm or just playing table tennis or playing tennis, you need to fine-tune our models. That's too complex and challenging to do some zero-shot results.
I see. So I guess after you are done with this training, how do you evaluate the results?
That's a good question. And we have many applications and metrics to evaluate world models or policy models. So in our experiment part, maybe in section 5. So we first evaluate on the sim prediction tasks. Like we can evaluate how good is the RGB prediction, and also for depth and normal modalities, since we have the ground truth for each dataset. And also we can measure the chamfer distance, one of the metric of point cloud. And also we do some applications for world models. Then we can evaluate the world models. So we do some action prediction tasks in RL bench simulator, like our model performs well and it's better than some 2D video world models like UniPy and other basically some 2D policy model like image behavior clone. We also evaluate, like, we can see that this is one of the application for TesserAct, is that novel view synthesis. Like, if we can generate a 3D point cloud, then we can render another view. We can render another image from another camera view. So we evaluate the novel view synthesis results here, and this is how we evaluate the world models. And like yesterday, Meta, they released their new world models, and they inspired me that we can also evaluate world models on next action prediction, like in the maybe text space. Can I say that? It's about
Yeah.
maybe a high level tasks can be, I want to arrange or make the scene tidy. Now the robot arm it's just opening the drawer, then what should I do next? So this is also one of the application for world model, but we don't evaluate this when we release the paper, but Meta inspired me for it.
Cool.
Yeah.
So did you
yeah,
compare?
this is the.
Have you had
Yeah,
time to compare to
we.
Meta at all, or no? Yeah.
You mean compare our model with Meta's model?
I know it came out yesterday. It's a little unfair.
Yeah, that's interesting. I think our model is better than their model, like for video prediction part. It's because they use vision transformer to predict next frames. In my view, that VIT maybe is worse than diffusion models in terms of generalization ability, and also their resolution is maybe 256. Yeah. But our resolution is about 480 times.
So it's almost
640, and it's high resolution videos. But their core idea is that they use world model to do many applications. This is their novelty, their core idea. And the inference time is really fast for the VIT. Like for the TesserAct or for the diffusion model, the inference state is slow. Maybe to generate this video may take 2 minutes on 100. So this is one of our disadvantage. But this is trade-off.
makes sense.
If you want to generate a high resolution videos, then you must take it.
Yeah, so
I suppose
it would make sense then if.
Sorry. Oh wait, okay, maybe I'll go first. So I suppose, like, at the limit, like, if these world models were to improve, I think one way the way you describe in the paper is that you can imagine this world model at inference time. Just imagine different scenarios, and then then the robot can, okay, maybe I'll take this particular path. But for it to be practical, I guess at inference you need to imagine really quite quickly.
Yeah.
Right. Sorry, Chris, you had a question?
Less of a question than a comment. It's more like it seems like the difference is if you wanted to generate robot training data or something like that. We've seen that suggested. Like it sounds like this approach with diffusion models would be much better because it's like higher quality rendering. Is that kind of that sound right? Yeah.
Yeah. Like there's many great base model for video diffusion called VideoX 1 2.1 are the best video diffusion. They are the best open source video diffusion models. So we can easily maybe get their knowledge. We can borrow their knowledge of models to enhance video prediction on robotics scenario, something like this. But for VIT model, there's not, for now, there are not great architecture for video diffusion in terms of generalization ability. But they can also generate high quality videos in the training domain. But if we want to move on some in the wild image, that may be hard.
So how you or maybe this is for Chris as well. I'm trying to rationalize at the extreme again when these world models get really good and a lot more compute efficient. What does it do in terms of, let's say, the overall data collection pipeline, right? So it strikes me that if you have a world model, which is basically a simulation, I guess in my view, you can generate a lot of synthetic data that it would be extremely hard, like costly to collect in the real world, right?
Yeah.
But at the same time, you also mentioned that actually to get to that good pre-training in the first place, you do need still all these, like, for example, 100,000 actual real-world videos. So you still need at least a non-trivial base of this data set in the real world in order to get the world model like pretty performant. So am I right to say that therefore, in summary, you still need pretty substantial real-world collected data with the real robots, but then you train up a very good world model, and then from there use the world model to, I don't know, 1000x the potential like synthetic data. Is that how you think this will play out?
Yeah. So like there's some constraints in real world data collection, like it's hard for real world robot to play maybe like playing tennis. But if you collect some real world data like grasping the cup, then mix with some data in simulator, Google robot playing tennis, then we can use world model to generate more videos, more data in real world, like a Google robot playing tennis in real world. This is what I find for our works. Definitely, we can train our model on real world and also collect some challenging data in simulator. Then we combine them to do some co-training, and the world model have ability to generalize cross different domain and generalize well. Then it can guide us to generate more video data and then enhance the robot control in real world. Yeah, that's a great idea and a great question.
Yeah, I guess as a follow-up to that, let's say even if you have trained up a very, performant world model that can really imagine anything you throw at it, right? You just describe in text, again, Google robot that is playing tennis.
Yeah.
I guess my question is, at that stage, then maybe it becomes like a limit of like what do you even ask the world model to imagine? Like, would you say then, then the next bottleneck is that, like, because I imagine there's a scenario where you ask the world model to imagine, like, I would say scenarios that may not actually directly apply to the real world.
Yeah.
Or rather, maybe the search space is so big in the real world. So I guess let me rephrase my question.
Sure.
Do you think that it's I mean, again, like if you ask a world model to imagine, let's say, a humanoid playing tennis, but there could be nearly infinite way for video model to imagine, right? At what stage do you think that it's become a meaningless use of compute and inference to generate those scenarios? Because I imagine the world model can imagine nearly unlimited. Where do you stop?
Yeah, good question. Good question. Like, so first, this indeed the features of world models, like based on the user's interaction, there may be infinite possibilities to generate different action or trajectories for a robot to picking up something or playing table tennis. And maybe in our future works, we are working on making this more controllable. Like, we will also give some camera position condition or some action conditions on our world model. Then we can control the robots in the video, in the imagination easily. Then we are more likely to generate the videos we want. So, like, for now, if we just prompt a TesserAct with playing table tennis, then there's many possibilities. Yeah. But I think this also not a disadvantage. Like, it's about diversity to generate different trajectories, like how we perform a task. But in the later, we will make this more controllable. So the robot arm can be controlled by some floating numbers, like the position of the end effector. Yeah.
I was going to ask about that,
that's
whether
a
or not you could
trade-off.
send in trajectories. Yeah, makes sense.
Yeah, but that's always a trade-off. Like, if you want to diverse generation results, and compared with a controllable, a more stable, like model, that's always trade-off. And maybe for stability AI, for Sora, they want a diverse generation results. But maybe for robot control, we want a stable results. Yeah, that makes sense. And that's indeed what we will do in the future to make the video generation more controllable, conditioned by many floating numbers or by many position of cameras, the actions performed by robot arm. Yeah.
Yeah, and I suppose, like, over time, even if you don't change your architecture, but the underlying, like, I mean, there will be a better cock video X, every few months, right? So as that underlying, video diffusion model improve, I suppose this will naturally also improve, right? Even if it's the same data set, same architecture.
Yeah. Cock video X improves a lot. Like, we try many video diffusion models before this one, and we find that the quality is really bad. And when we move to Cock Video X, it's a great base model. Then we can do many applications, do many modalities, adding many modalities to the base models. So the emergence of video diffusion models make world model great.
Makes a lot of sense. Very cool.
Yeah.
And
So I guess
okay,
maybe
you
if
go ahead.
I don't know, like is there anything more in the paper you want to highlight?
Yeah, there may be some technical details like many for the papers. They only add depth modalities, but in our paper we add normal as well. I think this is because normal can reveal some geometry clues for the 3D scene, like how smooth or like how smooth of a surface. Then it can help us to refine or improve the depth map. And we show an algorithm like how to use normal to refine depth map here, so we can generate a really great 3D scene. If we don't add normal, the result can be like here, like this image shown by sorry. And if we add normal to the reconstruction stage, the 3D scene can be great. Like the surface is smooth, the scene is well reconstructed.
But when you say normal, are you talking about just one normal, like one particular surface?
Okay. The normal is that it's like first the definition is of normal is that for this surface where it points at. So if we know this information, we can use them to improve. Like the prediction of depth map can be noisy. The surface is really noisy. Then if we know it's a surface and they all points to somewhere, then we can get a rounded.
So how do you get the normals? Do you compute them from the depth cloud, from the point cloud, or do you do something else then?
Yeah, we have two methods to get normal. For the synthetic data, we can just get them from the simulator, because
Right.
we know the precise steps. Then we can compute the normal. And for the real world data, if the dataset didn't provide any 3D information, then we use Marigold, which is the best paper of CVPR. We use Marigold to annotate these 2D videos and then generate depth map and normal map. So maybe in summary, we distill the knowledge from Cog Video X and Marigold and Rolling Depth, which is a video depth estimator. Then we combine their knowledge together to design and train a TesserAct. So TesserAct can predict these 3D and 4D images, and then we can use them to get a robot to perform action in a real world or in a simulator.
You did mention, I think in your, was it the limitation section, something about
Yeah.
the limitation being one surface. So that's why I was asking the previous question. Actually,
I
so
see,
what do you mean by that?
So, you mean the limitations or?
Under your limitation section, I read, I guess one of the main limitation is that you, let's
Here?
see. Yes, at this part, yeah. Yeah, single surface, yeah.
So the limitation now is that our model only predicts the single view videos. But if you want to reconstruct a 4D scene, you may need multi-view information.
Oh.
So for now, we can only get the depth map, the normal map from a single view. So it's not enough. So in the future works, we will do some multi-view diffusion models like
Oh, I see.
Cat 4D.
Okay. Yeah.
Like
No,
this is
sorry, I was a
our
bit confused because it was say single surface, and I just when I say the word surface, I just thought normal. But I guess what you meant is actually just different views. Okay, I get it now. I see. Okay, got it.
Yeah. So you can see that all the prediction results are single view. Promising, it's promising. We still need to enhance it. And also the video results shown here maybe a little bit simple. Like there's only one sponge, or the whole thing is too clean. So there's also some complex thing, and they're also generated by TesserAct. Like for this one, the image is from RT2, robotics transformer, and it's a teaser of RT2. So we prompt TesserAct to generate a video of picking up the apple by Franca robot. It can find the apple. But if it prompts some really challenging task like picking up the horse or picking up the dinosaurs, that may fail. Like our training data never see these objects. And also this is the teaser from diffusion policy, picking up the green cube precisely. But there's another limitations here, is that TesserAct cannot detect the robot arm originally in the scene. Like it will generate a new robot arm, but it cannot move the existing Franca arm in the image. This is one of the limitation. But I think it's more about data part. So we may improve this by scaling the data. And also this is captured from our lab, and it can just move the clothes from there to cover the book. And also it can pick up the pink chip bag in a really complex scene. And that's really promising. And also here's the video from Pydero. We just use one frame as our input and then prompt it to open the bottle. This is really interesting that they use URE5 as their robot, and our video results just add a Franca robot arm, on their base. Also we provide some results from movies or in
Sherlock
Breaking
Holmes.
Bad, or in Inceptions. So it can generalize really well, and also some fun results, like in the Van Gogh paintings or in the Ghibli movies.
Yeah, I really like the painting examples that you have.
Yeah.
Well, I love the Studio Ghibli myself. Yeah, the TV delivery. Yeah.
Yeah.
Oh yeah, that one's.
So when I get these results, it was like, so that's really a great improvement for the embodied AI community. And there are many papers are doing the same thing, like Zhen proposed by NVIDIA. And also yesterday, Meta introduced their VJAPA 2 world model. We are all doing the same thing. But for our work, we trying to make the world model 4D. That it.
So what do you think would be your top like lesson for all these people? Because yeah, like you're saying, like world models are very exciting right now. Lots of people working on them. What do you think is the best lesson for all the other people working on this from TesserAct, from what you've done?
Yeah, I think world model is really a architecture or a great idea for robotics. Like it can guide how robot arm perform actions or how it move in a really complex scenario. There's many challenge here, like how to train the video diffusion models, like how to get a great generalization results. We may need many GPU resources, takes many times to train, to find the proper hyperparameters. Yeah, so it's promising, but it requires more resource.
Yeah, I mean,
Makes
not
sense.
just the compute. I think the data set as well.
Yeah,
I mean,
yeah.
and I guess the other thing is also like for example, the Kiki delivery, like towards the end, it's very impressive that you have an anime scene and then but you have a robot that pick up the cup.
Yeah.
But at the same time, I'm also thinking in the real world, if Miyazaki were to draw this scene with a robot, the girl would definitely move right to stay away from the robot. So understanding, because in this scene, like the girl is a dynamic person, a being or agent, which can also interact when there's a robot in the scene. So I think those kind of understanding will take quite a while. I imagine a lot, actually a lot of real world data set to even do the pre-training well. And then of course like huge amount of compute.
Yeah, data is another question. But we find that we only train the TesserAct on like RT1 datasets, bridge datasets, but we can transfer this knowledge to another domain, like in animations, complex scene. Then we can generate more data by this world model. Like world model, maybe we use a lot of robotics data collected by one institution to train our world model. But once we have this powerful world model, we can use it to generate more and more data in another scene. And I think this is why many research institutes test world model recently. So they are also the great data generator with some not diverse data to generate diverse robotics arm performing action in the scene.
All right. I guess, to wrap up the episode, usually we like to ask a final question like, is there any like cool paper you come across recently you want to give a shout out to that maybe our listeners can also go and take a read at that paper?
Yeah, you mean for papers in robotics?
Any kind of paper, actually, like that you think it's inspire you. Like it could be nothing to do with world model, but you just want to give a shout out to.
Let me have a think. I will recommend maybe 2 papers, or one is the one video. For now, they are one of the best video diffusion models in the world. They can generate videos like physics or some people dancing and the physics are correct, something like this. So they are the best diffusion models, And for our future work, we may use 1.2.1 to train a new world model. And another one is that Zhen, proposed by NVIDIA. They use world model to generate data, and they also have a policy model to generate some policy from this predicted video. Then they use this new data to train their GROOT, their famous robot policy model, and find that there's a great enhancement in robot performance. So this really inspires me. Like they use world model to generate more data to train their robot better. And then if we have a better robot, then we can collect more video data to train our world model. That's really promising for me. Yeah. So they really inspires me. So I would recommend these two papers.
Yeah, very cool.
Yeah, awesome. Yeah, I guess that's a wrap. Thank you so much, Haoyu, for sharing.
Mhm.
I think lately the recent episodes, I think I find the multiple of our recording have something to do with world models. It's definitely
They do
a
come
very
in bursts.
active area of research.
Yeah.
Yeah, but thanks so much for sharing. We look forward to your next update. Yeah. Maybe
It's a very
TesserAct too,
unique
I
take
guess.
too. It's very cool. Yeah.
And maybe TesserAct too.
Okay, cool.
Cool.
All right, Chris. What do you think? What do you think of this paper?
So I think we've seen a lot of world model stuff lately. I think it's a really exciting area of research. But I really like about TesserAct personally. I like the addition of like the 3D features, the normals, and the depth, and the video prediction. It's like it's a unique take. I could definitely see those helping it generalize. The results look really nice. I think like I said, it's a unique take on a very exciting area. Cool work. What did you think?
Yeah, it seems to me that, like you said, he mentioned something like if he didn't have all those projector, right? Basically, depth projector, normal projector,
Yeah.
like basically the whole thing would just break down. So I think like careful design about like what model to like he used like rolling depth, he used marigold, right, to basically further like pick up specific data modalities to pick those out. I think it strikes me that it's still takes a human being with a very good sense of the real world to figure out what would be the good so-called data modalities or features to abstract out and then focus on that.
Yeah.
So definitely nowhere near so-called end-to-end.
Right. And recovering things like the normals is also a little bit tricky, like as it came up when we were talking with him, right? So like, because it's not just a natural thing that you get from a depth camera, right? Necessarily, but like, yeah. I also thought it was interesting. It's an interesting approach though. Yeah, definitely.
Yeah.
Yeah.
Cool. Yeah, I guess we'll have a lot more.
Yeah. We have more stuff on. You just dropped off. More stuff on. World models coming up. Is that what we're gonna say?
World model. Yeah.
There's a lot going to be a lot on world models.
It's like nonstop.
Yes. Yeah. That's the exciting thing. Like we're all like, and it's one of these interesting debates right now. Yeah. Oh yeah. There was this recent talk by Ken Goldberg in IEEE about like the robot data gap, which I think maybe where it's like pi. I can bring up the exact numbers, but this is relevant. It's like.
Yeah, but I mean, again, I always wonder, like, are we in a local minima where, like, we think that data and scaling solve everything? I just keep coming back to this, like, mosquito intelligence. Like, I call it mosquito intelligence. Like, the mosquito probably have used very, very little compute and probably have, collect, like, a very, very little sample, I guess, before it starts to fly and be really good at flying to the point that you basically can't kill a mosquito because they fly. They're so agile. So I wonder, how much of it is just more compute, more data versus just a very different way of looking at the entire problem. But yeah. I mean, maybe, some of the work from, for example, Edward John's group in Imperial College, we had a chat with him. All these in-context learning things, very, very data efficient, it seems. Yep. Well, in a way, world model is a simulation. Yeah. In a way, world model to me is another simulation. It's simulation in a very different way from the usual classical. Yep. Okay. Anyway, okay. We'll until the next one we'll chat again. Yeah.